Welcome to our help video on part 4. And in this one, we're going to build atoms, and then we are going to change the atom into a positive ion called a cation by removing electrons. Remember, cations are positive. The way they're positive is because a cation's lost negative electrons, leaving it with more protons than electrons, giving it a positive charge. It's the transfer of electrons that takes place during chemical reactions. The first one we're asked to take a look at is sodium 23. They told us 23 is in hyphen notation. Sodium 23 is telling us they want the sodium atom specifically that has 23 particles in the nucleus. They also gave us the nuclear symbol. And in the nuclear symbol, the mass number's on top, the atomic number's on the bottom. If you remember, the mass number is abbreviated by letter A, the atomic number is abbreviated by letter Z, and if we're reading the way some languages do, top to bottom, we would go A down to Z. Mass number down to atomic number. Just to be sure that this atomic number is right for sodium, we can check the periodic table of ions, or periodic table of elements. Here's sodium right here. It's in the first column, which we call first family or first group. Its atomic number's right here in the upper left-hand corner on this particular periodic table. So on the periodic table, they can put the atomic number anywhere they want. But in the nuclear symbol format, the atomic number is lower left-hand corner, mass number, which is telling you the total particles of the nucleus, is upper right-hand corner. Now, they didn't want us to build this one. You're like, why didn't we have to build this one? That's a fair question. Why didn't we build this one? Well, here's why. If we start, we said we needed 11. 1, 2, 3 is lithium. 4 is beryllium. 5 is boron. 6 is carbon. 7 is nitrogen. 8 is oxygen. 9 is neon. 9 is neon. 9 is fluorine. 10 is neon. I'm out of protons. I needed 11 protons to match my atomic number. So I could not build this one because they didn't have enough to build it. But we do need to know something from this. This level, we already learned that inner level, the one closest to the nucleus, called the first energy level, slang term first orbit, holds 2 electrons. The second level will hold 8 electrons. That's the most it will hold. And when we get to the when we get to another electron, I would have to have a third level. I'd have to add a third level. So when we're looking at building sodium, we need 23 particles in the nucleus, or not building sodium, but drawing sodium. We need 23 particles in the nucleus. 11 of them are protons. So 11 protons in the nucleus. If I have 23 total particles in the nucleus and 11 of them are protons, 23 minus 11 would leave us with 12 neutrons. If I start off with 11 positive things, then I need 11 negatives to balance that, so it's a neutral atom. They want us to start off drawing a neutral atom. So here we go. I need 11 electrons placed in here. 2 go on the first level. That's why there's a 2 here. Now, you didn't have to put in the little dots for the electrons or little circles for the electrons. I did just because I think it's fun. So 2 go there. Now, I have more to put in. I need 11 electrons. So I put 2 in, so I have 9 more. So 8 of them are going to go on the second level, second energy level. That's all it will hold. 2 plus 8 is 10. I need 11, so I have a third one that I put out here. Later, I crossed it out. But originally, I had a third electron out here. Why did I cross it out? Why? There was 1 electron, and I removed it from the level. Here's why we did it. Let's continue reading on. How many electrons were in the middle orbit? How many electrons did we put in the middle orbit? The answer was 8. There's my middle orbit. That's the second energy level. How many electrons did we place on the third level? We had 1 there. We had 1 there. So there was 1 electron on the third level. Now it's asking us to look on the periodic table of ions in order to see the charge above sodium's column. Here's sodium. Periodic table of ions says that sodium wants to become 1 plus when it reacts chemically. But it wants us to look at the Roman numeral above sodium's column. So I go up, up, up. It's a Roman numeral 1, and there's a 1 plus written underneath there. What does that mean? Well, we had 1 electron on the 3rd level, and it's Roman numeral 1. In an earlier video, we noticed that the Roman numerals seem to correlate or match up with how many electrons there were on the outer level for the neutral atom. The outer level for sodium was the 3rd level, 3rd energy level. It had 1 electron there, and it has a Roman numeral 1 above its column. So what's the relationship between the Roman numeral and the electrons in the level furthest from the nucleus, which we call the valence? Valence is the level furthest from the nucleus. It was the level that you were last putting electrons in. They're the same number. Why is it plus 1? Let's take a look. There was an electron here. We had 11 protons, we had 11 electrons. To make it negative, or to make it a positive ion, excuse me, to make it a positive ion, I have to remove one of the negatives. So for it to be positive 1, I need 1 more proton than electrons. So if I have 11 protons, I need 10 electrons to leave it with 1 plus. So when sodium chemically reacts, another atom from some other element will rip off that electron on the 3rd level. Why would that happen? Well, it leaves it with 10 electrons. What atom has 10 electrons? If we go back and take a look, what atom has 10 electrons? Let's go back here. The atom that has 10 electrons is neon. Sodium starts with 11 electrons. If it loses an electron, it has the same number of electrons as neon. It doesn't become neon. The only way we can get sodium to become neon is if it gets a proton removed from the nucleus in a nuclear reaction. Nuclear reactions mess with the nucleus, but in a chemical reaction, it only can mess with electrons. If sodium chemically reacts and loses one of its electrons, it'll have 10. We know neon is in the inert or noble gases, meaning that they are chemically stable. For some reason, 10 electrons is chemically stable, and that's what sodium will want to do. They react to become chemically stable. Taking a look at this, we can see why it wants to happen. It's left with 8 electrons. If it loses the 1 in the 3rd level, it's left with the 2nd level full. 8. 8, an octet. Oct means 8. Smaller atoms are stable with 2. Larger atoms are stable with 8. So by losing 1, sodium's left with 8. It's left chemically stable. That's why sodium has a plus 1 written right there. That answers most of the questions on this page, I believe. It does. It has the same electrons as neon. The next one they're wanting us to do is calcium. Mass number 40, so we need 40 things in the nucleus. Again, this is going to have more things. We won't be able to build this one. The model builder won't be able to build them this big. So we need 40 things in the nucleus, but I have to look at a periodic table to get the atomic number for calcium. I need the atomic number. Here's a periodic table of ions. There's an atomic number in the left-hand corner. So calcium needs or has 20 protons. Any atom with 20 protons is calcium. So 40 things in the nucleus. 20 and 20 is 40. If 20 of them are protons, 20 of them are neutrons. If it starts with 20 positive things, we need 20 negative things to balance those out. The 20 protons will be balanced with 20 electrons. 2 fit on the 2nd level. 8 will go, or 2 fit on the 1st level, 2 fit on the 1st level. 8 will fit on the 2nd level. 2 and 8 is 10, so I need 10 more. In the information you received in green writing on your little, in your lab notes or lab sheets, it said to put 8 on the 3rd level. Now the 3rd level holds more than 8, but it says put 8 on the 3rd level, then start putting the rest on the 4th level. So we put 2 on the 1st level, 8 on the 2nd level, 8 on the 3rd level. That's 18 total. So 2 will go out onto this 4th energy level. So there's an electron there and an electron there that I later crossed out when we got to other questions. Speaking of other questions, let's take a look at some of the questions we might need to answer here. How many electrons did we end up with on the third level? 8. Slang for third level is third orbit. How many did we have on the fourth level? 2. Now it's saying, what is the Roman numeral above calcium? Here's calcium right here in the second column. It's called group 2. The Roman numeral above there is 2. So once again, the Roman numerals are matching up with the number of electrons that it had on the outermost level, which we call the valence. They're the same number. One's written as a Roman numeral and the other's written as a regular number. It says that calcium likes to become 2+. Let's see what happens here. When calcium likes to become 2+, you're like, where did you get that it likes to become 2+? There's 2+ right there. There's 2+ right there. When calcium becomes 2+, it loses 2 electrons. If it loses 1 electron, it would have the same as potassium. If it loses 2 electrons, it has the same as a noble gas, which is stable, inert, chemically stable. That's how many it wants to have. All the atoms want to end up with electrons the same as the noble gases have. So we now can see if calcium loses those 2 electrons, it will have the same number as argon. Argon has 18. 2, 8, and 8 is 18. But look, when it lost those from the fourth level, it's left with 8 on the third level. 8 octet. That is the number they are all trying to accomplish. Now we're going to do aluminum. Again, we can't build aluminum using our model builder. Aluminum that we're supposed to build has 27 things in the nucleus, of which 13 of them are protons. So aluminum has 13 protons. If there's 27 total things, 27 minus 13 means there must be 14 neutrons. This one starts with 13 protons. It'll end with 13 protons because in chemical reactions, protons are not changed. And we're sure that's the correct number. If we look on here, there's aluminum right there. Underneath there is the number 13. So aluminum has 13 protons. It starts with 13 electrons. 2 go on the first level. That's the most it can hold. 8 will go on the second level or orbit. That's the most it can hold. Then we'll put 1, 2, 3 on the third level. It has 3 on the third level. Now they're going to ask us to look at the Roman numeral above aluminum. The Roman numeral above aluminum. Here's aluminum, group 13. These numbers are just going left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Those are group numbers. Aluminum is in group 13. But they're also called families. The vertical columns are called groups or families. The family Roman numeral is right up here, 3. Why does aluminum have a Roman numeral 3? I think we can see aluminum has the Roman numeral 3 for the same reason that it has 3 electrons on the outer level. The Roman numerals are telling you how many electrons it has in the valence or outer level. We could see that if aluminum loses these 3, 1, 2, 3, it would be left with 10 electrons. So aluminum would want to become 3+. Aluminum would want to become 3+, as it says right here. As it says right here. When aluminum becomes 3+, if it loses 1 electron, it would have the same as magnesium. If it loses 2 electrons, same as sodium. If it loses 3, it would be the same as neon, a stable, noble gas, chemically stable. Why is it chemically stable by losing 3? It's because the inner level would be left with 8, part of the octet. In the octet duet rule says 8 is good for the bigger levels, 2 is good duet for the innermost level. If it loses those 3, it's left with 8, a stable octet. It seems like all of them are trying to get the same number of electrons as Roman numeral 8, which is the last column to the right. Our last column to the right, the noble gases have the Roman numeral 8. And that is it for this question.